Okay, so good afternoon and thank you for being here. I am Osmar Zaiane. I'm a professor in computing science. I've been at the university now for 20 something years. I'm also the director and a fellow at the Alberta Machine Intelligence Institute. This is an institute working on machine intelligence, or machine learning in particular. And we've been in existence since 2002. So I'll be talking about artificial intelligence, so the promises and the perils of this field. And I will have three parts. So today we'll be talking about what is AI, the past and the present. In 2 days, so I'll talk about part two, which is, I'll talk about I give a cautious view towards the future. How will AI allow us to do things? And part three, I will go deeper in what we call machine learning to show you how a machine can actually learn to do things. Let me first try to bust a myth, first of all. It is largely believed that computer scientists like me, and particularly artificial intelligence specialists, assume that human intelligence is more or less solved and that machines will soon replace humans. Well, this is definitely not true. Even though duplicating some of the intelligence equal or superior to ours is one day inevitable, actually human intelligence is more complex than many would think. Yes, with the new paradigm like deep learning, and I'm sure most of you have heard of this deep learning, and I will talk about deep learning later, we can make the machine do amazing things that seem very clever. But deep learning, which is currently stealing all the attention and has the limelight on it, it's still very limited compared to, let's say, sentient human beings. We, as humans, we are a ball of emotions, and our actions are not just dictated by our brains, but also our hormones and the microbiome in our guts have a say in the way we behave and make decisions. We are not always rational, by the way, but we function, let's say, in a smart and astute way compared to other animals. So I believe if we do not end up self-destructing, I mean, we destroying the whole planet before we manage to do that, because we are indeed a vicious and selfish animals, we will eventually have a machine that is as intelligent, if not more intelligent, than humans. But in my opinion, in my humble opinion, unless we have some major breakthroughs soon, we are still far from that moment in the future. It'll happen, but I don't think I will see it myself. So I will give you a very simple example. Humor. If I say all humans are intelligent, but some are asymptomatic, I don't see people laugh, but this is referring to, so this is referring to the condition we live in. So COVID-19, we're talking about people who have COVID-19, but they're asymptomatics. That means that they don't show the signs of COVID-19. They don't cough, they don't have a fever. And when I say all humans are intelligent, but some are asymptomatic, that tells you something. But you understand as a human, because you put it in the context, even though I didn't talk about COVID-19 before, but we live it, you understand the joke. It's a joke. I just made it up. Well, I didn't just make it. I made it up a few days ago when I was thinking about this. For computers, it's not trivial. So this being said, we are making incredible strides in the direction of, well, super intelligence with machines. Um, However, as someone in the field, I work in AI, I can feel the acceleration. So we're going towards that, and it's getting faster and faster. We are making and contributing innovations on a daily basis, basically. But at the same time, we are also discovering and realizing the complexity and the sophistication of what we call human intelligence. It's not that trivial. Okay, so let's try this. Oops, no, that's not what I wanted to do. So what do you see here? A mannequin. Let's dress this mannequin with the COVID-19 attire. Oops, that's not what I meant. A suit. So this is what I will call a COVID Zoom attire. It's a joke, guys. You should laugh. Are you machines or are humans? Well, machines can't understand that. They don't understand the humor. Humor is one of the most sophisticated forms of human intelligence. It requires semantics, interpretation. It requires knowledge, sometimes culture, knowledge about the culture of the people that you talk to, and certainly timing. I mean, some jokes work now, but they wouldn't have worked a year ago. Okay. Even sometimes, if you ask the comedians, they will tell you timing is essential. When you tell the joke makes a difference, not just about now or last year. Is it in the beginning or at the end of our conversation, for example, can make a big difference. And computers don't understand humor. They can't create humor, and they can't even recognize whether it's a joke or not a joke. Particularly sarcasm is extremely hard. Sometimes it's difficult for humans too. Let's say something else, another joke about COVID-19. So in 2019, it was recommended to avoid negative people. Negative people are bad. In 2020, we recommend to avoid positive people.
Yeah.
So if I tell this joke to a computer would not understand that it's a joke and would not make the connections with positive, meaning positive, having COVID-19 has been tested positive. But we have this ability to connect things in different ways. So each one of you connected it in a different way and realize it's a joke and may laugh about it or may not laugh about it. Okay. Yeah, so the humor is very hard for computers. So what I'll be talking about today is what is this AI? Also, what is machine learning? AI is not new, so why now? Why now we're talking about it and it's a big, big deal and the promise is bigger than ever before? If we have time, and I don't think so, because in the past when I gave this talk to this class, we didn't have the time and I ended up putting it in part 2, I'll be giving some examples, particularly in precision health, how this can be used. Okay, since this course is in the context of a course in medicine, I give examples in health. Okay, let's go to what is AI. And most of you know or think you know what AI is because we built little by little a definition in our head. But I hope I will help you have a better picture after this lecture. So what is artificial intelligence? Artificial intelligence has been coined in the 50s. So in 1956, to be more exact, a conference was organized by researchers, mathematicians, statisticians, and computer scientists. It was the beginning of the field of computer science. They, some of them were adamantly convinced that anything we do with our intelligence can be broken down into pieces and each piece can be independently coded. And then if we put it all together, we will recreate intelligence. So we can write programs that do like we do, we as humans. And they convinced funders. This is when they called it artificial intelligence. They convinced funders, and they did this first conference to try to plan basically how to do this. This was a big deal, and there was a huge hype about it in the 50s and 60s and 70s. People thought, oh my gosh, now the war is over, Second World War is over, and we have these computers, we can do them, I mean, we can make these amazing things, and if we can create intelligent machines, we'll rule the world. So this is part also of the Cold War. The Russians wanted to do it as well, of course, and many other places in the world. The expectation was huge. So to prove this, they never managed to prove it actually, but what they tried to do is try to solve problems that obviously would need intelligence. At least this is how we look at it. For example, playing chess, playing checkers, playing backgammon, all these games that we know would require some form of intelligence to play and win in particular. So they mimicked the human intelligence in the computer by playing these games. But there was a disillusionment, and people lost hope. This doesn't work, and the funding dried out. Some people continue to work on this, nevertheless, and in the 80s, there's a subfield in the field of artificial intelligence, a subfield called machine learning, that focuses on teaching a machine to do something without explicitly programming that something in it. Here I'm giving an example of, for example, detecting in email what is spam, what is non-spam, and the machine has to learn by itself. This brought back hope, because this machine learning, and I'll explain it a little bit later, allowed us to solve many problems in many domains. It's only in the late 2010, so in 2012 and more particularly, there's another subfield within machine learning called deep learning that uses artificial neural networks that manage to do to provide amazing results, and I'll show you examples later. So, what is interesting to remember from the slide, and I'll repeat it here, is that in the field of computer science, we have a subfield called artificial intelligence. I made it here big because I'm going to zoom in. But there are many other fields in computer science, like networking, high-performance computing and parallel computing, software engineering, graphics, database management systems, algorithms, human-computer interaction, and so forth. There are many subfields. One of them is artificial intelligence. Today is so important that any university teaching computing science, they have courses for undergraduate students on artificial intelligence. So it's part of computing science. You can't dissociate it. Within artificial intelligence, you have also many subfields. One of them is called machine learning, as I just mentioned before. But there are many others, like planning, knowledge representation, reasoning, computer vision, natural language processing, and many others. There are also subfields of artificial intelligence. So if I zoom in now, I did it bigger here for machine learning, doesn't mean that machine learning is more important than knowledge representation or reasoning. I made it bigger because I'm going to zoom in again. There are 3 subfields or major classes of machine learning. There's what we call supervised learning. There is unsupervised learning, and there's reinforcement learning, and there are other smaller ones too. And again, within supervised learning, I'm going to zoom in. There are many different techniques to supervise a machine to learn. One of them is called deep learning. Okay, so deep learning is one technique, one paradigm inside supervised learning, which is machine learning, which is artificial intelligence, which is part of computing science. Okay, so the three that you need to understand is the deep learning is machine learning, which is AI. Okay, so what is this AI? Here you have an artificial brain. Well, a representation of I didn't do that. It's from an artist that I don't have the name. So what is artificial intelligence? Everybody's using the term now. You open any magazine or any newspaper, they will talk about AI. You'll see many documentaries and movies and blogs, and everybody's using now the term AI. And it seems important. Why it is important? Because people are claiming like, oh, the market with AI will be worth $60 billion by 2025. So it's obviously important. We should know what it is. And you have some people who are saying, oh, well, the one who dominates AI will actually rule the world. You have an idea who said that? No? Well, it's Putin. Putin said that. This is a quote from Putin. And if Putin says that, he knows what he's saying. It's important. And that's why now we have a race. The Chinese are investing in AI. Canada is investing in AI. US is investing in AI. Germany is investing in AI. Everybody's investing. Because indeed, if you dominate AI, there's a high chance that you will rule the world. However, even though now it seems to be very important, ruling the world and $60 billion, this is big. What is AI? So most of us get the definition from these magazines and newspapers of journalists. They're not really specialists. Even worse, we get our definitions from science fiction movies, Terminator, you name it. There are so many other ones. And unfortunately, movies are the wrong source for these definitions. They media as well, they portray an unrealistic picture of what AI is. What is that picture? Well, typically the pictures are, well, AI is going to eliminate us. It's the machines against the humans. And AI is dangerous. And it's not just the media and it's not just the movies. You have actually famous people saying that too. And now we believe it. Unfortunately, this machine against humans, them against us, creates fear. Fear of some, especially when we don't know what AI is, we fear what we don't know, and we see AI as an existential threat. The truth is that AI today, what can AI do today? Well, check your pocket, you'll see a smartphone. That's the level of AI we have today. So the fact that it can recognize your voice, you can give commands, it can predict the next word that you're typing when you're typing your text. It corrects also your mistakes. It can predict the next action that you're going to do, things like that. When you're typing, it knows, oh, that's a phone number. Do you want to add it in your contact list or something like that? That's the AI we have. It's definitely not a threat. Okay, so what is this AI? Okay, not the movies. Forget the movies. That's the wrong idea. One of the pioneers of this field, who was there, one of the organizers of the conference actually in 1956, is Marvin Minsky. Marvin Minsky died recently. He was the founder of the first AI research lab, the AI lab at MIT. And he defined it as artificial intelligence is the science of making machines do things that would require intelligence if done by men, by humans. So Minsky doesn't say anything about feelings and emotions of the machine. Remember, I said that we humans are actually a ball of these emotions. Minsky doesn't also talk about the intention of the machines, to that matter, okay? So we make the machines do things. The machines don't take initiatives for now, anyways. So here's a definition. Artificial intelligence is a discipline striving to get machines behave intelligently by performing tasks that would normally require human-level intelligence. Okay. So AI is not, certainly not our enemy. It's an extension of us. I see it as an enhancement of our creativity. It's a tool. Okay. It's a tool that allows us to do things with more ease. Things that we didn't do well, now with this tool we'll do better, or things we couldn't do and now we can do. Okay, and I'll show you examples. The interesting thing is that AI is a moving target. Not a long time ago, there are things we called artificial intelligence, and now we take it for granted. It's not AI at all. I'll tell you and give you an example. A while ago, we used to use typewriters. I don't know if you know what a typewriter is. So we typed letters with a typewriter. We typed documents. I can tell you my first thesis was with a typewriter. All my essays were with a typewriter, and justifying text was hard. You had to calculate the words before you start the line. You calculate the words and the letters, and the leftover, you put it into spaces between the words. If you made a mistake, you had to go back and use the liquid paper and erase it. And it was complicated. So the day they invented word processors, they were machines specifically for word processing. It was considered as artificial intelligence because it can find mistakes. It can justify automatically, just type and boom, it's justified left or right or perfectly justified. It's amazing. People say, oh my gosh, I was spending hours to do this and now it's done in a few minutes. Who thinks today that a word processor is artificial intelligence? Nobody. We take it for granted. So AI is a moving target. What we think is complex today, and we solve it with AI, after a while, it's not complex anymore. It's not AI either. And we take it for granted. So AI is a moving target. Okay. In addition to AI, there are other words that we use, and they're very close. There are terms like data mining. Have you heard of the term data mining? Yeah, there's also data science, data analytics, business intelligence. These are all very close. Big data. Everybody's talking about big data, and particularly in medicine, because we have so much data. So what is data mining? Okay, data mining has been around for a long time as well. So I did my PhD in the 90s, and it was about data mining. Data mining is a process of discovering and extracting potentially useful and previously unknown patterns from large collections of data. So the question is, you have a lot of data and you want to discover. So it's something that you didn't know about. And what do you discover? You discover these patterns. Patterns, and the patterns can be represented by formulae, can be represented by rules, can be represented by different things. And hopefully these patterns are useful. So they're potentially useful. What it means is they're actionable. I can use them to take action. Okay. It's the analysis of data and interpretation of data in order to provide actionable knowledge for decision makers. And the decision makers can be humans or can be another machine, another algorithm that uses these patterns in order to make decisions. In reality, data mining is at the confluence of many different fields. One of them is artificial intelligence. So you have databases to collect the data, you have information retrieval, high performance computing, statistics, you have to visualize these patterns, so visualization is important. but AI is also part of it. And data mining is at the confluence of all these, many other fields as well. Okay. So in addition to data mining, there's also the field of data science. Often now we use them all as synonymous, but they're not really. So it's a multidisciplinary field. Also, we use algorithms like in data mining to extract knowledge and insights from data. But it also deals with storage of the data. How do you store a lot of data and be able to share it, integrate it when you have data coming from different sources? How do you integrate it together, and so forth? So it encompasses a little bit more than just data mining. Here I'm representing it visually. You have databases, of course, statistics as well, the whole of computer science, and data science sits in the middle here. Often it is synonymous with many other words like data mining. They make them synonymous, but actually they're not really, but it doesn't really matter here. Business intelligence, big data, they're all used interchangeably, unfortunately. So let's go back to AI, artificial intelligence. As I said, it started in the 50s. But at one point, nobody was talking about AI, and now it's coming back in force. And everybody is mentioning AI. We're talking about AI in our television, AI in our toaster, AI in our remote control. And I'm not joking, and actually many of those are using AI. It was a joke in the 80s, but now it's not a joke anymore. Actually, you have remote controls. I may use it as one of the examples later on. Remote controls that use AI. So they know what kind of channels you want to watch and those that you don't want to watch. So why is it coming now? There are three main factors. Why now? Factor number one, we have a lot of data, and AI is hungry for data. It learns from data. And now we have the data finally. And I'll get back to that. There's another factor, which is the fact that our computers today are very powerful compared to what they used to be. So they can crunch all that data to find these patterns and learn from the data. And the third factor is the development of new algorithms that are able to take advantage of the data and take advantage of this high performance computing. Okay, so I'll zoom in each one of them to show you what exactly is happening. So where is this data coming from? Well, we have, just look at the interaction you do every day. You send emails, you like things on Instagram or Facebook or whatever. You share things. You post them again. You search on Google. You tweet. You read news from the different sources you have, and you share them again. You share your images on Flickr and others. You share your videos. So there's a lot of data. So I have here an image. This is quite old to show the different activities I mean, the amount of exchange on every single one of these data sources is flabbergasting. It's huge. Let me show you another example that is a little bit maybe more concrete in health, because people measured it in health. They've been measuring it for years to show that it's an issue. In healthcare, we're collecting data from even things you don't think about. So we have sensors. If you go to the ICU, you have sensors everywhere to measure temperature, to measure blood pressure, to measure this and to measure that. All that information, each bed is sending an incredible amount of data. So you have also the electronic health record. You have information about the insurance. You have information about the clinical trials. You have genome data. You have even data on social media. We are using it now to assess the mental health cases in the population. So we use it in public health, for example. So et cetera, et cetera. In 2011, people have estimated So this is already a few years ago. In the US healthcare system alone, just the US, they estimated that they were collecting 150 exabytes, and soon it will reach the zettabyte level. What is an exabyte? Well, 1 exabyte is equal to 1 billion gigabytes. Do you know what a gigabyte is? It's a lot of data. Well, this is a billion, not a million, million, so a billion. It's a lot of information. Sorry, zettabyte is a billion. The other one is a million billion. Anyways, it's a big number, huge. So some people try to visualize it. So what is the billion? I don't understand what that is. So there was a paper, I think it's in 2011, looking at data that they collected about healthcare system in the US. Actually, at that time, they were looking at the whole data that they could access in 2007. So they wrote it in 2011, but it's about data in 2007. And at that time, in 2007, 2008, 9, 10, we were using CDs. So they said, okay, if we calculated this big number. What is this big number? Billion, million, whatever. If we were putting them in CDs and we stack these CDs one on top of the other, and knowing that a CD is 1.2 millimeter thick. So how many CDs do we need? And if we stack them, how high the tower will be? And they realized actually that tower of CDs will reach the moon. That gives you visually an idea about the amount of data we are collecting. And that was 2007. When they published in 2011, by then that information was obsolete. And there was another paper that focused just on health data in the US. And they said, okay, forget the CDs. Now we have DVDs. On DVD, you can put way more than a CD. And they said, okay, let's do the same calculation. If we put them on DVDs and stack them one on top of the other, well, they will reach the moon twice. So this shows you that it's an explosion, exponential explosion. The data is growing very, very fast. In 2007, it was all the global data. 2011 was just the data on healthcare in the US, and it's way more. Okay. So to better understand the phenomenon, what is happening here with the data, let me illustrate this with SD cards. You probably use, I don't know, probably nobody uses now cameras. You're using your phone to take pictures. But for those using cameras, we still use these SD cards to store data. And to show you the progress, in 2005, the largest micro SD card, so micro SD cards are smaller SD cards. The largest one was 128 megs. In 2014, so a few years later, it became 128 gigs. And it doubled 2 years later. Today, you can buy, I mean, this was last year, but I couldn't find this year a bigger SD card. You can reach 1 terabyte on a small, tiny, I mean, this is the fingernail size. You can put a terabyte on a fingernail-sized one. So we went from 128 megs to 124 gigs. 1 terabyte is 124 gigs, so 1,000 gig. So it means we increased in 14 years 8,000 times. We can cram 8,000 more data in the same space. Okay? And that's why we store a lot, because we can put in a smaller space, we can put more data. In addition to that, it's becoming very cheap. It's almost free. What do you mean almost free? I'll show you an example again. This is a picture taken in 1956 for a big deal. IBM found a customer who was willing to pay to buy a 5 meg hard drive. 5 meg hard drive. If you take a picture with a good camera that generates a raw file image, that file is more than 5 megs. Just one picture. That disk was so important that even the captain of the airplane was there for the photo op, because nobody has seen a hard drive of 5 megs. That hard drive of 5 megs was $120,000. Okay. Today, you can buy, that was actually 2 years ago, you can buy a 64 gigabyte SD card for 18 bucks. So that's an increase. I mean, incredible. If I take a decrease, not an increase, if I take that 64 gigabyte hard drive, SD card, it's not a really hard drive, it's actually a chip, and I go back in time and go to the past in 1956, with the costs that we had for 5 megs, this 64 gigabyte will cost $1.5 billion. $1.5 billion, now I can buy it for 18 bucks. It's difficult to fathom. The improvement is phenomenal. That is equivalent to 76 million times. Of course, in more than half a century, 62 years, but still 72 million times cheaper. And that's why it's free. I can store anything I want. And that's why we don't delete anymore. We store, we don't delete. Okay? And we have all that data, we can use it for AI. Okay, so that's about massive data. Now let's talk about high performance computing. I said that we improved a lot. What does that mean? Well, here's an example. This is what we call a GPU. Do you know what a GPU is? It's a graphical processing unit. It's a card that gamers love because they can add on their computer to play games, and it improves the performance of the computer because it renders, it's specifically designed to render graphics. The G is for graphics. Okay, it renders graphics on the screen. So who buys this graphics card? Are gamers. They're people who do design and like architecture and things like that, or design in 3D for designing pieces or engines. But it's now a commodity. People buy it. It's not that expensive. A card like that is about $1,000. Of course, you can find lower end ones like $300 or something, but a very good one, around $1,000. What does that mean? Well, that GPU is equivalent to this machine, a Cray 1, that was in the 80s. And in the 80s, it costed about $10 million. And very few countries had access to it because it was embargoed. It could have a military activity, blah, 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 and usage and stuff. So only the allies were able to buy it. The government had to say yes or no. Now anybody can go and buy the same power from a small store to add on their computer at home to play games. Okay, it's difficult to understand. So I'll show you here a graphic, interesting graphic. This shows since 1993, when I was doing my PhD, till almost today, so in 2019. I didn't update it for this year, but it's very similar. It shows the best computer in the world. Okay, so this is a website called top500.org. It ranks the fastest computers, the 500 fastest computers in the world. Okay, but every now and then there's a new computer that beats all the others, and so that's what you see in the graphics here. So the brown triangle is the fastest computer that year, and here you can see the performance in terms of how many floating point operations per second it can do. That's what we call flop. And then you have megaflop, gigaflop, petaflop, teraflop, and so forth. Remember, a mega is a million, a giga is a billion, tera is 1,000 billion, peta is 1,000,000 billion, and so forth. Exa is 1,000,000,000 billion. So for many years here, from 2016 and many other years here after the other, the Chinese had the best computer, the fastest computer in the world. It was 94 petaflops. So that's 1,000,000 billion floating point operations per second. Huge, okay? And the Americans were not very happy because they lost the top position. Finally, in 2018, the Americans beat the Chinese, and now they had the fastest computer in the world, 122 million billion floating point operations per second. That's amazingly fast. Okay. Now in 2020, this year, they managed to get peaks of 200 petaflops. Okay, the same machine. But they didn't celebrate very long. Immediately after reaching this record, the Japanese beat them. On June 2020 this year, the Fugaku, this is a computer from Fujitsu, reached 413 petaflops. So this is 400 million billion floating point operations. And actually they peaked at 1.4 exaflops. Exaflops is a billion, so 1.5 billion operations per second. It's amazing how much that is. Now, what does that mean? To put it in perspective, this is the Fugaku, or the new computer. It has 7 million CPU cores. So each core actually has 22, each CPU has 22 cores for the one that they used. And on total, about 7 million cores. These are units to do these operations. And the energy required is 22 megawatts. There's a lot of power. I mean, you can run many homes with that. IBM Summit, the one that used to beat the Chinese, has 200,000 CPU cores, and it also was running GPUs, 27,000 of those GPUs, okay? And it used 13 megawatts. That's a lot of heat. Now, what does that mean? How does it compare to the human brain? Do you know how many neurons we have in our brain, a human brain? So the human brain, an adult human brain, has about, well, between 100 to 90 billion neurons. And what kind of power it requires? 12 watts. 12 watts is like 1/6 of a normal light bulb, which is 60 watt. So our brain doesn't require a lot of energy, but these monsters, they need a power plant. And that's something important to remember, okay? So we're still very far from what this incredible machine, the human machine, can do, okay? Yes, they can do all these operations per second, but oh my gosh, what can you do with these operations, number one? Number two, it requires a lot of energy, okay? Now, that wasn't the point I wanted trying to make. What I wanted to show you is this progression, okay, this phenomenal acceleration. So let's go back to this graph. And if you look in your pocket and you look at your smartphone, where's my smartphone? Like this smartphone here, everybody has a smartphone. What is the fastest smartphone today? I don't want to do any advertisements here, but the fastest smartphones are in the order of 1 teraflop. So 1 teraflop in the graph is here. Okay, I don't know if you can see my mouse. Okay, so what computer was there in 1997 that reached the 1 teraflop? It is this machine here, the ASCII Red. And the ASCII Red, well, required 800 kilowatt, but it used a lot of space. Here you have a picture of it. The consumption was equivalent to 800 homes, and the cost is $55 million. Again, very few countries were able to afford that and were allowed to have it. Today, you have it in your pocket. So it's equivalent to, where's the smartphone? Let's look for it. Well, there it is on the desk. Okay, that smartphone here on the desk that I just put is equivalent to this whole room of machines. in just a few years. Okay, it is phenomenal. Okay, let's go back here. So what is this progression? Let's go back to 1994 or 1993 when this graph started. This is, let's forget the Japanese computer, go back to the IBM one because I have the data from 2018. So this is the machine, the fastest machine in 1993 when I was doing my PhD. Between 1993 and 2018, and remember this is a logarithmic scale, it's equivalent, so the progression in 25 years, the progression is equivalent to 206,000 times. So today's machine, the fastest machine today, is 206,000 times faster than the fastest machine 25 years ago. What does that mean? How can you visualize that to have a better grasp of what it means? What is this progression? Well, if when I was doing my PhD, whenever I walked, my step was equivalent to 1 yard or 1 meter, let's say 1 meter, okay? If my walk, my gait and my walk had the same progression as computers, today, after training for 25 years, my step will be 206,000 times more than a meter. What does that mean? It means today, if I make a step, I would be able to go anywhere in this circle with 1 step. Can you imagine that? Can you imagine if the human was able to do this progression the same way we did with computers? Now let's use that same metaphor with the memory, like the space that you need to put data, like the SD cards. 8,000 times the progression. That means in 1 step, I can do 8 kilometers from U of A here. I can go beyond the West Edmonton Mall with 1 step. Okay, forget the space. Let's look at the money. The value was reduced by 76 million times. That means with 1 step, I can go around the world twice. I mean, it doesn't make sense. Of course, it's nonsensical, but it gives you an idea of the progression. It's a huge, huge progression. Since you were born, I mean, the power of computers were multiplied many folds. The price dropped many folds. The space required dropped many folds. Okay, so it's and the progression continues. It hasn't stopped. Okay, so that's why today, well, actually, the price is even more than, I managed to find 128 gigs for $21, so even less than this price. But anyways, what I want to say is that we have a lot of data, and you can see that. We have way more power, and I'll talk about the algorithms very soon. If you're curious, I learned this actually a few days ago. Do you know how the old computers used to be? Which one is the oldest computer, the programmable computer in the world that is still in existence? Do you have any idea? No? Well, most people, even the experts, if you ask them, they will tell you the oldest computer in the early days, that was ENIAC. ENIAC is the electronic numerical integrator and computer. Why is the first one now? Because it's American. In 1946, this is after the Second World War, it was built and it's still in existence at the University of Pennsylvania, so in Philadelphia. And it's very important for many reasons. And today it's celebrated every year on the 15th of February. It's called ENIAC Day. Because actually it celebrates the women who were operating this computer. So not only one programmer was required, but many, we call them operators. Why women? Because at that time, women were specializing in dealing with switching the switchboard for the telephone, and they knew how to program the switchboards. And these computers were programmed the same way. You can see here is like a switchboard for the telephone, and they had these cables, and they're connecting them. So the first programmers in the world were women. So to encourage women to join computer science, today we have a huge imbalance. Unfortunately, we are actually telling them about this to encourage them, because the first programmers were not men, they were females. But unfortunately, this is wrong. They're wrong about the fact that ENIAC is the first computer. And by the way, you can see here the power of this computer. It could do 385 multiplication per second and only 40 divisions per second, or 2 square root operations, or 3 square root operations per second. Okay, we're not talking about the petaflops and all that stuff that we can do today. This computer was extremely important to calculate trajectories of missiles, and this is the beginning of the Cold War. Also, all the calculations required for the atomic bomb experiments and things like that. But the first computer is actually a German computer. The Nazis created a computer, the Z3. This is the Z4. The Z4 was not ready by the time the Russians invaded Berlin, came into Berlin, and the Germans, knowing that, they moved it secretly to Bavaria and hid it in a town in southern Germany. So it wasn't used during the war. The goal was to use it for calculating trajectories of the intercontinental V1 and V2 missiles. I don't know if you know the history of the Second World War. But at the end, it was confiscated, between quotes, by the French, and they were using it for their calculations for their atomic bomb experiments. And then later it was used for civil projects, like calculating all the engineering required to build a dam and things like that. And if you look at the power, it was able to do 1,000 floating point arithmetic operations per hour. Not per second, and those were huge machines. So that shows you the progression is phenomenal, incredible. Okay, let's go to, so we talked about data, we talked about high performance computing. What about powerful algorithms? Well, we have powerful algorithms nowadays, like deep learning. Okay, deep learning is actually not a new technology that existed also from the 50s, trying to simulate how the human brain functions. We didn't know, we still don't know how the human brain functions, or any brain. We have hypotheses, but we know the components, like the neurons, and we know how the neurons function. So they try to simulate an artificial neural network. And in the early days, with the early computers, we didn't have enough power to run complicated structures of these artificial neural networks. But today, thanks to these amazing computers and thanks to the data to learn from, we can have very sophisticated architectures of these neural networks to simulate what we now know better about the brain. And I'll tell you more about that later on. Actually, I have it here in some of these slides. So if you look at a neuron in the brain, and as I said, we have about 100 to 90 billion of them. It's a cell that receives a message from the dendrites. Okay, dendrites are connected to the different synapses from different other cells, other neurons, and it goes in the body of the cell. And then at one point, the body of the cell sends a signal along the axon, and the axon will connect to other synapses of other cells. So you have a layer after layer after layer of these neurons, and they pass on the message. So an artificial neuron is like what you see here on the screen. So you have a cell, we call it an input function, and it receives signals coming from the synapses from the other cells. Each signal has different strengths, so we have weights. So you have few of them here, I call them M, and each one has a different weight. They come inside here, and at one point there is an activation function that decides to fire a signal, and you have an output that goes, and that output becomes one of the M other connections for another layer with another cell, and so forth. So we organize them into layers. There's one layer called the input layer, that receives the first input, like I'm watching an image, that's my input. And then from that input layer, these cells communicate with a hidden layer, we call the hidden layer inside, and then it may connect with another hidden layer, until it goes to the output layer. The output layer will give you the final signal. And thanks to today's computers, we are able to put many, many, many layers. In the past, they said, okay, we can live with just one layer because we can't run more. We don't have enough power in the computer. But now we can have many layers, and that's why we call them deep. We call it deep learning because of these many, many layers. Of course, this is very simplistic. I have many layers and they are all interconnected. Every single cell in this layer connects with all the cells on the next layer, and every neuron here connects with all the cells in the other layer. But in general, you may have other architectures where you don't have full connectivity, but you have selective connectivity. You have different layers that specialize in different things. So there are many, many different architectures, and I won't go into details. This is the field of basically deep learning. And the field, the fathers of this new field, deep learning, are actually in Canada. The first one is Jeff Hinton from the University of Toronto and Joshua Bengio from the University of Montreal. So we're proud here in Canada to say that we are the source of this technology in the world. There are other people as well, like Jan LeCun, who was a postdoc of Jeff Hinton. He's one of the directors at Facebook, and there's also Jürgen Schmidhuber who invented the LSTM, one special architecture for deep learning. How did it happen that now people are focusing on this deep learning? What's special about deep learning? So deep learning, as I said, is a rebranding of a technology that existed from the 50s called artificial neural networks. But people forgot about it. It wasn't that important, except some pioneers who persevered and kept on working on it, like Joshua Bengio and Jeff Hinton. Okay, all the others forgot about it and dropped it. Wasn't important. But there's one event that changed everything. And today you have deep learning in every single an industrial thing, like, for example, the phone. The AI that works in the phone is based on deep learning. So what happened? Well, in 2012, a team led by Jeff Hinton and his students, so his students, there were, I think, 2 students or 3 students, and Jeff Hinton participated in a competition. So this competition has been running for a few years. Every year you have different teams competing. And what do you have? You have millions of images of all sorts. And you have to automatically classify them into groups. These are cats, these are dogs, these are buildings, these are horses, these are flowers, whatever. There are, I think, 22,000 categories. And then the teams were ranked based on how many correct classifications they do, okay? So here's the graph. In 2009, the accuracy of the winner was around 70%. 2010, a year later, the winner was better than the previous year, so they're almost 72% accuracy. And then 2011, they got an accuracy of almost 75%. So they were advancing little by little, and they were using the classical techniques of machine learning. We'll talk about machine learning later. Then 2012, what happened? You have a team led by Jeff Hinton and his students. They used some GPUs that were people were using them to play games. They used them to do calculations that they wouldn't be able to do with the CPU. To do what? Well, to simulate all these artificial neural networks running in parallel to do these calculations. The neural network that people forgot about, but Jeff Hinton and his students kept on working on. And this is the result. They jumped directly to 83% accuracy, almost 84%. And then people who are using the traditional machine learning, the classical techniques, say, oh my gosh, what happened? So they put aside all these classical techniques, and everybody was focusing now on artificial neural networks. That was rebranded as deep learning. So the year after, actually, Google has hired the team of Jeff Hinton from Toronto. They asked them to create a company, and they acquired that company for an incredible amount of money. And everybody was trying to see if this new technique can work in industry, and indeed it worked in many, many things, and I'll mention it. But you can see that now year after year, they improved, and now they do better than an expert human at recognizing these images and categorize them. So when Google hired these students and Jeff Hinton, they said, let's try this on real stuff now. We have images that we collect from the internet, and we have the best search engine. We have access to billions of these web pages. Can we use your technique to, for example, recognize automatically cats and dogs and label them automatically so that when people look for an image of a cat, I can return that quickly? And indeed, they had incredible results. Okay. And I said, well, okay, you tried it on this competition for images. Now we tried it also with image. Can it work with something else? Well, yes. There's another competition from DARPA. DARPA funds many research related to defense. And there was this competition that started years ago from the 90s. They have a lot of data from telephone conversations. So you record people talking on the phone, and you want to transcribe this into text, okay? So you had a lot of people listening to this and typing it. It takes forever when you have thousands and thousands of hours of phone conversations. So they wanted to do it automatically, and they started this competition where you have many companies competing because they want to get the market, the contract with the military. And this is now a graph showing the error rate. It's not accuracy, so the lower the better. And you can see that where they improved year after year, but then they plateaued. All these are different techniques from different companies. They plateaued, and when you see that in the after the advent of deep learning, when people discovered deep learning, they tried it on this data set, and then it started going down, 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 and now the error rate is lower than what a human gets. So these machines using deep learning to transcribe automatically from voice into text are better than humans. And that's exactly what happens on your phone now when you get an automatic message that people leave you on your voicemail, and then it goes automatically in an SMS. It's using these techniques. They tried it also on all sorts of things, like detecting objects in an image. Again, they do better than humans. This is for translation. They're still far away from automatic machine translation. I mean, we're still far away from humans, but they're improving significantly thanks to deep learning. Also, they are trying to answer queries. So they give you an image, and they ask you to describe what's in the image. They don't tell you find the dog and which image has a dog. No, they give you an image and say what's in there. And then the machine will say, well, somebody walking next to a bicycle crossing a street, something like that. Okay? They use deep learning to do that. Of course, we're not as good as humans yet because it depends upon the data that you give it to train. But it's improving quite a bit. Well, you think, well, that's it. Then deep learning can do everything. Well, I'll show you some examples where there are some issues. So as I said, they try to deploy it in all sorts of applications. Here's an example of an application. Who can tell me, you can unmute and tell me, what do you see here?
Sir, the dunes of a desert.
Desert, dunes, yeah. That's good.
Sand.
Sand, yeah. Cool. See, humans are good at that. Well, the British police was using AI with deep learning to spot porn. because they wanted to stop these pedophiles exchanging images. And basically, this was detected as a nude. These dunes were detected as a nude. So obviously it's a failure. You, Eduardo, you had absolutely no problem saying it's a dune and it's sand. It's a desert, but the computer had problems. I'll show you another example. Who can tell me what this is? Have you ever seen this before? No, you've never seen it. I'm sure, well, not so sure, but very few people know about this one. What is it? Who can tell me what it is?
It's a car.
It's a car, yeah. How do you know it's a car? Do you see the wheels? No. But somehow, by analogy, you guessed it's a car. Do you know if it's the back or the front?
The back.
The back. You also know it's the back of a car. Well, do you know what deep learning will tell you? It's a horse. It's a horse because there is the logo Ferrari. That is a horse. It's not a cat, but actually it's a difficult car because it almost looks like an insect. The lights in the back are not conventional. The shape, the design is not the conventional car. Let's turn the car. Let's see the wheels. So if I turn the car like this, do you recognize a car? Yeah, it's a sports car, a very nice car. But if I give it to deep learning and say, what is it? It'll tell you it's a horse. No, actually, it'll tell you there are horses. Okay? So deep learning still makes mistakes. Here are some other examples. When I ask it to describe an image, it may say a soccer player is kicking a soccer ball. It's not bad, but is the soccer player really kicking? No. The other one, a street sign and a pole in front of a building. Is that true? Well, if I look at the depth, I can actually imagine that there is a street in between the sign and the building. So it's not really in front of a building, is it? And then third one, a couple of giraffes standing next to each other. Are they standing to each other? I can see as a human being, I can guess the depth. One is smaller than the other, but actually they're not smaller. They have the same size, but because of the depth, one looks smaller. And actually the base, one is higher than the other. So I can extrapolate and imagine one is actually far from the other. They're not next to each other. Okay, so we still make crazy mistakes. We have to admit, it's not always easy. For example, if I give you this image, are these puppies or bagels? What are they?
Both.
Both.
Some are
Maybe,
puppies and some are...
how do you recognize here? Is it a Chihuahua or a muffin? It's not that trivial. And if you put in the image both, it's even more complicated. What about this one?
Oh my God.
Watch out what you bite, because it can bite you back. What about this one? So, of course, people have been studying and testing this and trying to push the limit. Okay, but even humans, we have to admit, even humans, we have trouble. Okay, it's not a trivial task. Now, there is also a lot of people working on attacking systems like that because they want to prevent these attacks. Suppose I am now implementing a deep learning system like this to detect the signs for the self-driving car. I want to recognize a stop sign from the no left turn sign, from watch out, there's work in progress or whatever. And I don't want people to intentionally spray something on the sign and then make me believe something else, okay, an attack. Or maybe not intentional. If there is a storm, a snowstorm here, for example, in Canada, and you have snow on the sign, how do you recognize it? Okay. So I'll show you examples of attacks. So here you have a panda and you have a gibbon, okay? So with deep learning, you take an image of a panda, obviously it is a panda, and deep learning recognizes it as a panda, and it says, my confidence is 57%, okay? The confidence of the algorithm is above 50%, 57%, which is quite high. It's not random because I don't have two classes. I have many, many animals. So confidence is not bad. And it says it's a panda. Now I add noise to the image. And this noise that I add to these pixels, you will not see it. So it results in this new image. The third image here is the same panda, but with some noise attached to it. If I now ask the same deep learning, what is this? It'll tell me, oh, it's a gibbon, and I have 99% confidence. So the confidence is extremely high, and now it believes it's a gibbon. That's a problem. There's another typical attack as well. I don't know if you can see this kind of, it looks like a cell with a Golgi apparatus and mitochondria and whatever, but if you take this image and you superpose it here, you put it next to the banana. In the beginning, I had the banana alone, and the deep learning says it's a banana with high confidence, and it may be a slug or a snail or an orange, but very low probability. But very high probability it's a banana, so it's confident it's a banana. Then suddenly I add this image on top next to the banana, and then now it tells me, oh, it's a toaster. Very, very high confidence it's a toaster. I have very small confidence it's a banana or a piggy bank or something else. I don't know piggy bank because it sees like slots here. So you can see that you can fool the system very easily. Okay, we have to be very, very careful with these systems. Now, what is machine learning? I talked about deep learning, and I said deep learning is part of machine learning. What is this machine learning? So machine learning is basically a means to make machines learn from data. So they analyze the data, interpret the data, find patterns in the data that discriminates between classes, so I can adapt to that data as data changes. So data is seen as an experience. I learn from it. What do I learn? I learn to predict the future. So I adapt to the environment. If my future changes, I can adapt to it. For example, I can learn from experience by looking at images of dogs and cats. And somebody tells me, these are dogs, these are cats. These are dogs, these are cats. Afterwards, I will see a new image that I've never seen before, and I will predict whether it is a cat or a dog. Okay, so that's how they do for recognizing these images, for example. So deep learning is one of the techniques to build this learning model, but there are many other techniques. It requires training. So I will give it some data that is labeled. Labeled means this is a cat, this is a dog. Somebody tells me, or this mammography has cancer, this one doesn't have cancer, and so forth. Lesion is a melanoma, this one is benign, and so forth. So the data has to be labeled, and I learn from that labeled data a predictive model. So basically what you have to remember, you have data that is labeled, I go over it, and I will create a classification model, or a model that will predictive model. That model now can be used for labeling automatically new objects that have never been seen before. Okay, we'll see examples later. So one of the models could be a neural network. Deep learning is basically building a neural network to learn what discriminates between the different classes, what discriminates between a dog and a cat and a gibbons and a panda and so forth in the images. There are other paradigms for learning that are not necessarily requiring the same kind of training data, but they need experience. For example, reinforcement learning. And if we have time, I'll talk about reinforcement learning very briefly, because reinforcement learning is the specialty of U of A. So U of A is the mecca of reinforcement learning in the world. So we are known here at University of Alberta for the reinforcement learning. And I'm sure Patrick Pilarski will speak also probably after me. So part 4 will be Patrick Pilarski. He's one of the specialists in reinforcement learning. He works on building artificial limbs, so prosthetics basically that can adapt to the people with using reinforcement learning. So the message here is that AI is way more than just deep learning, even though people talk about deep learning all the time and is becoming almost synonymous to AI, but it's not. Okay, deep learning is a technique in machine learning, which is one subfield in AI. But something interesting about deep learning, very interesting compared to many other techniques, traditional techniques, or old algorithms, let's say, in machine learning, is that, and I'm just representing here in a simple figure, this is performance of the algorithm of learning. And this is the amount of data, so this is performance, this is the amount of data that I give the algorithm for training. Previous algorithms, when you increase the amount of data, they actually perform better, they perform better. At one point they reach a plateau and they don't improve. You give them more data, but they don't improve. It's like they don't know what to do with additional data. That's all I can learn, that's it, I'm saturated. However, deep learning, the more data you give it, the better it gets. It gets better, it gets better. And that's why at one point, it does better than the humans. It learns more than the humans. But to reach there, you have to look at millions and millions of images. Now, even though deep learning can recognize a cat from a dog very easily, it required millions of images of cats and millions of images of dogs to reach that level. A human being, for a child, you say, that's a cat, that's a dog, that's it, they learned it. Okay, so the way we learn is certainly not the way these machines are learning. I don't need that much data to learn. However, well, at least they can reach levels that surpass the human being for some tasks. So I'll show you some examples of applications very briefly. I'll go in depth later for other examples. You all use emails. In the early days, emails was, well, it was a nightmare with all these spams that we were getting every day. And people started creating rules to detect these illicit emails that we were getting. For example, if it talks about buying this, then it's spam, put it in, delete it. If it uses this word, then delete it. But of course, the spammers knew how to adapt to those rules and they could circumvent those rules. So the rule-based filters for spam filters were useless. Instead, people used machine learning, showing examples of spam and examples of non-spam, and let the machine learn by itself. Then it knows how to discriminate between the two, and then when you have a new email, it'll label it by itself automatically. The beauty is that I can do it for each individually alone, because what is spam for me may not be spam for you, it may be interesting, and what is spam for you may be interesting to me. So the machine learning is actually built in your interface that you use to read your email, and the training is observing you. It observes you what you delete without reading and what you save and respond to and so forth. That seems to be interesting. So it builds a model that adapts to you and automatically filters the spam. So the spammers cannot adapt to every single one because it's not a simple rule. Okay, so it's way more efficient. Another example that you use every day is when you go to the bank to ask for a loan. They use machine learning to look at all the previous cases, characteristics like age and their salary, whether they own a car, they don't own a car, they own a house, or they're renters or whatever. And then they look at whether they paid back the loan or they defaulted on the loan. If I give enough examples of this to the machine learning will build a predictive model. Now, when I'm going to the bank and they ask me questions about, do I have a car? What kind of diploma do I have? Am I married, not married? All these characteristics, they enter it in the machine. The machine will predict whether actually there's a high probability that I will default or that I will pay back. And then they will approve or not approve automatically, okay? Of course, all this happens behind the scene. They don't necessarily tell you about that, but that's exactly what is happening on the machine of the clerk that is actually giving you the loan. Same thing is happening whenever you go and buy. Now you use your credit card to buy something. When you scan your card, there is a transaction that goes for authorization. Do I authorize this transaction, yes or no? And there is a machine learning algorithm that looks at your previous transactions, how you behaved buying transactions or not, and then will flag this transaction as potentially fraudulent or not. Okay, it learns from data that was labeled, this is fraudulent, this is not fraudulent. Okay, this happens in a fraction of a second. In healthcare, there are many examples predicting diagnosis, prognosis, the treatment, the recommendations, all sorts of things, and I'll show you some examples next time. Here's an unusual example that people don't think about, how machine learning can be useful in medicine as well. So all my examples are on purpose selected for medicine. This is the case of paraplegic. So paraplegic cannot use their hands or their feet or whatever to control a wheelchair. So somebody else has to do it for them. But instead, what we do here, we have sensors that are put on, I mean, in a helmet. It's not a helmet, it's like a bonnet. They put on a hat, they put on the head, and it reads the brain activity. So we train this machine by giving it data. So what kind of data we give it? We ask the patient to think about wiggling the toe. So they think about wiggling the toe. They can't move the toe, obviously, but there is an activity that happens in the brain that we track and we give it as data to the machine. Then we say, whenever you want to turn right, wiggle the toe. So we have that activity, and that means turn to the right. When you want to turn to the left, move your left hand. They can't move their left hand, they're paraplegic. But by thinking about it, they have a different activity than the one for wiggling the toe. Same thing for stopping, same thing for going backwards, going forward. So now they can give commands to the wheelchair just by thinking about it. Okay, we can do exactly the same thing for a cursor on the screen. So these paraplegic people can now write without the help of anybody except the machine. They just have the letters in front of them on the screen, and then they think about turning left, turning right, going up, going down, and the cursor moves. And then they have a thought for enter. Enter could be, I don't know, moving the other arm or something like that. But it's trained for every single patient. And the machine can adapt to their input and basically allow them to write and so forth. This is with machine learning. You can see that machine learning can change the lives of these people completely. How much time do I have? Oh my gosh, I went too fast, too far. Let me introduce very quickly reinforcement learning, and then I'll let you ask me questions, and then we can finish there. So reinforcement learning is completely different. Instead of giving examples that are labeled and we build a predictive model, it's a different context. It's based on behavioral learning. So it's trial and error. And I try things. If they work, I will do them again. If they don't work, I will not do them again. But how do I do that? It's basically like training an animal or training well, humans are animals too. When you want the dog to roll, you say roll. You give a command, but they don't roll. One day they will roll and you will give them a reward. So now each time you say roll, they will not get a reward unless they really roll. Then they will associate the order to the action that will give them the reward. Okay. Same thing with the children. You say, don't do that. And they know that you're serious and you're angry, that, oh my God, I'm not going to do it. If you say, oh yeah, nicely done, you give them a reward, a biscuit or whatever, then they know that they want to please you, they will do it again. Okay. So that's what reinforcement learning is about. You reinforce the learning by giving some reward. So you have a world. So there's an agent that lives in a world and interacts with that world. How? It takes actions. And whatever it takes actions, the state of the world will change and a reward is given to them. The reward can be positive or the reward is negative. Negative, it means it's bad. And that exchange is the experience. So again, visually here, you have an environment, you have an agent I'm representing as a robot, but it can be as a program basically. And the program has a set of actions that it can take. It will choose an action randomly in the beginning, and then using that action, it will change the state of the environment. And then there's an observer, the program itself, that will say, okay, this is the new state of the environment. And by the way, I will give you this reward for that action. So it will do it many times with some stochasticity, of course, some randomness there, but it will learn a policy that maximizes the reward at the end for a set of actions that it takes. And the pioneer in this technology is Rich Sutton, who is at the University of Alberta. I don't know if Rich Sutton will present this year. In the past, he also gave talks in this lecture, in this course, but Dr. Solis will confirm that later. So how this can be used, Patrick Pilarski will probably talk about these adaptive prosthetics. So these are prosthetics that we add to people who lost their arms or legs or limbs in general. And instead of having a hook, you have a very sophisticated robotic arm, but it's not just the patient adapting to this new prosthetic, but the prosthetic can also adapt to the human with these actions and rewards that it gets. For example, I can predict whenever I am driving, if I start moving my arm slightly to the right, it's because I'm going to shift gears, for example. So my fist starts opening already, rather than having the robotic movement to very artificial. It becomes smoother. It becomes like a human movement. Okay. So these are the kind of things that reinforcement learning can do. I'm going to stop here, and next time we'll talk about more cases, and then I'll go to the future of what can AI do in the future. Okay. Any questions, guys? Then I can drink some water.
I have a question about if I think it was deep learning or machine learning takes into account the input over time and then it perfects itself. What will happen, or what do you think will happen when we begin programming for feelings? Because the feelings that some humans will have about X situation may be the opposite feelings that other group of humans have about the same situation. How do you predict that the machine would fix or correct for that to guide its compass, if that makes sense?
So first of all, deep learning is one of the supervised learning techniques that are in machine learning. So machine learning is a more general term. Reinforcement learning that I just mentioned, that learns with this experience, with the rewards and actions, is in the same level as the supervised learning, and deep learning is part of supervised learning. That's very high level kind of description because now they interact. Actually, reinforcement learning is using a little bit of deep learning as well, and now we call it deep reinforcement learning, but those are details that are too complicated to get into now. Typically learning, it doesn't continue to learn unless you stop and retrain. So it learns from training data, then you deploy it. And we'll go in details in part 3 when I'll cover the techniques for machine learning. So you give it training data, it learns from that, and then from there on, it will just do predictions based on what it learned. Now, there are other techniques that allows it to keep on learning as we go. So you give it more data and it keeps on learning and keeps on improving. Those are very, well, they're specific techniques. You're talking about feelings and they change from one person to the other. And you're talking about feelings that may change from the one person in the morning and the afternoon is different. So if it changes from one person to the other, it's not a big deal because you build a predictive model for each person. Okay. Or you predict a generalized kind of model and then you adapt it with a little bit of data for one person and it adapts to that person. The question is, what if the person himself, I said in the beginning, we are a ball of emotions and our actions are not dictated just with our brain, but our hormones and even our guts. We change. I mean, we are not rational and very consistent. So that is a little bit more complicated, but it can also be done because we can, the thermostat in the house, like, well, I don't need to name the companies, but everybody, well, most of you probably know that there are thermostats that can learn to adapt to you in the house. So it knows when in the morning you prefer to have it cold or warmer, and when in the evening you want to increase your temperature and so forth, by observing how you increase the temperature. And you may have different people in different rooms who may have different preferences. So there are techniques that can do that, and the same idea can be done with this change of feelings, as you call it. So it is possible to use predictive models to do that. It can be done with reinforcement learning, and it can be done with reinforcement learning. Will do many mistakes, so you can do it in simulations and then you deploy it, or you can do it also with supervised learning like deep learning. Now, detecting feelings is a big topic. This is what we call emotional intelligence. So how do you make machines emotionally intelligent? We humans are emotionally intelligent. What does that mean? It means I understand when you are sad, and I can realize when you're happy, and I can realize when you are surprised, and can act on that. So if somebody is sad, I want to show empathy. So I also show emotions and I react with emotion. So that's what is what we call emotional intelligence. And to make the machine emotionally intelligent is not trivial. So there are many techniques to detect emotions from faces, but also from speech. So when people smile, if faces is relatively, well, it's difficult, but it's relatively easy, but people also are working on the words that we say, because sometimes I don't see the face, but I can hear you, or I can see the text that you write, and we can detect emotion. Now we want the machine not only to detect emotion, but also to express emotion. Because to be emotionally intelligent is not only detected, but also expressing it. So there's work on that. My team in particular is also working on that for the case of chatbots. But yeah, it's another subfield within the field of AI. Other questions? Nicole, Khadija. It's either too complicated or too easy, or you're still surprised.
Sorry, I know we are like over time, but I was thinking, like, it was interesting to see how much storage do we need to store this data in case we wanted to, get further to have a, kind of intelligent human that's actually not a human being. What do you think about how could that be operated? And, you know, for data mining, in terms of data mining and data storage, how would that, could that be something applicable, or as you said, it's still far away?
So data is not a problem. We have a lot of data. Storing it, as I said, is now free. It doesn't cost. It's very cheap, relatively cheap, and it's also it doesn't take a lot of space physically. I can store it in small, tiny spaces. What is difficult to get is labeled data, data that has been labeled. So, for example, just to I can get a lot of data about medical images. But to get medical images that are labeled, this has cancer, this doesn't have cancer, that is way more complicated because it's not available, because of privacy, because of all sorts of things. So getting training data is the difficult part. Data itself is not a problem. Data mining needs a lot of data. And that's why we need data mining, because it's able to go through large collections of data that we humans cannot analyze. Okay. But the training is an issue. I don't want to have a lot of data to train for something to be accurate enough to deploy it. As I said, kids can see a cat for the first time and recognize a cat the next time they see it.
Mm-hmm.
I don't have to show kids millions of images of cats for them to finally say, aha, now I know the cat has whiskers, has these ears, and so forth. So people are working on techniques to reduce the amount of data that is required for training. Not reduce the amount of data. Data, we have it anyways. It's the amount of data required to learn a model that is predictive, that has good accuracy. So there's a lot of techniques that people are trying that are not supervised, so unsupervised. Unsupervised means I don't need labeled data, but we're not there yet. It takes a while. So for example, in reinforcement learning, I said it doesn't need a lot of training data, but it still needs a lot of experience. So experience, I'm not gonna release it in nature and say, okay, go and learn, because it will make so many errors, it'll make a mess. For example, I can teach a helicopter to fly by itself and do flips and all sorts of things. So if I use reinforcement learning for it to learn how to do these flips, and I just release it, it'll crash so many times. I need millions of these helicopters because I'll lose them all. So the way we do it in a simulation. It learns in the simulation. Once I learn the policy in the simulator, I put it in a helicopter and I release it. So even in reinforcement learning, we need a lot of experience. So people are still trying to come up with new methods that will have the same accuracy, the same kind of learning, but with less experiences and with less, not just experience, with less also training data. We're not there yet.
Okay, sounds good. Thank you very much.
Okay, well, thank you for a great teaching session, and we look forward to Thursday.
Thank you. See you on Thursday.
Yeah.
Bye, guys.
Bye-bye now. Yeah.